Shall I? Go. Hi, Ernst, and everybody who's watching online. Thank you for being here. For those who haven't seen this before, we are a weekly networking event where we offer presentations on the subjects of technology and design. We're weekly here, so do check out our website to see what the programming is going to be for the next couple of weeks. It's ehvinnovationcafé.org. And today we have Danqing Liu here talking about soft robotic skin. I hope you enjoy it very much, and thank you for being here.
Thank you for the introduction. My name is Danqing Liu. I'm assistant professor at Eindhoven University of Technology. I'm working at the Department of Chemistry and Chemical Engineering. Today I will talk about soft robotic skin. And most likely your background is not in the chemistry, but I hope that I have enough video to amuse you that you can appreciate the effect mainly we are created here. So in our research group, we are emphasized on advanced materials for the application of soft robotics, haptics, and optics. I'll touch upon mainly on the soft robotics, especially and on the surfaces. So when people talking about soft robotics, you can sometimes see the video like this. This is a typical soft robotics. We are working with a researcher from Zaragoza University. That you see this yellow strip is a thin polymer film that can deform under stimuli, for example, heat or light or other stimuli, and deform. And this deformation can also grab a weight, like you can see here, and lift it. Now, also some other form of soft robotics, like if we have the a small strip go from the flat to cone shape, and we also use this to making a suction cup that under the light stimuli, the cone becomes flat to press the air out. Then we create a vacuum situation, and a small little polymer film can pick up and device. And we can further to integrate this to the soft robotic arm that can pick up the ball and lift it and even rotate it to the desired position and eventually to lift, to drop this object. This is so-called a standalone soft robotics. But for the field, or for you maybe start wondering, the material is soft, and you can see this is a real-time video, doesn't look too fast. So the underlying drawbacks of using soft robotics is really it is soft, doesn't exert much force as your traditional robotic system, and also it kind of slow. To solve this question, we are asking ourselves how to broaden this field of soft robotics. Then our solution is that going from 3D to 2D. This means that instead of looking at the standalone element, we are looking at the coating surfaces. In a robotic system, we are mainly interested in create dynamics at the coating surfaces. The dynamics can be, for example, you can see a film going from a flat state to the state with pre-designed topographic pattern. And we can switch this on and off, or eventually continuously. We use this for haptic application, I will discuss later, and also use this for material transport. Besides mechanical create surface dynamics, we also can do in the chemical way, which means that if you're looking at this video, we can eject a liquid from the bulk of the coating to the certain coating surfaces. And for today, I will emphasize those two effects. I come to in more detail. Now, a little bit background on the materials we are using to realize this soft robotics. It is not a strange material. It is the material that you actually use in your display. That's liquid crystal display. We are using exactly the same molecule to realize that. Only instead of looking into the optical property, we are looking into the responsiveness, mainly go to the mechanical properties to realize various applications with this material. Now, with liquid crystal, what you see here is that the advantage is that you can have various orientation of your molecule, which means you can control how you want to the molecule organize. Either they form a twist along the axis, or they twist 90 degrees, or they also can bend over along the thickness. And for liquid crystal, I would like to emphasize we're using as a polymer film. So for all of the rest of work, you're going to see there are piece of polymer film that you can touch, you stretch, like you encounter the daily. Now, a little bit about mechanism before I show you the application is that using liquid crystal, we go from the ordered state. This is the ordered state. This row represented molecules. They are very well aligned. What we are going to do is to decrease the alignment or decrease the order of the molecule orientation. By decreasing this, what we have is expansion along this thickness, which is perpendicular to the molecular direction, and contraction parallel to that. But now, since we are looking at the coating, we restrict the implant deformation. We're mainly looking at what has happened at the surfaces. You will directly see some of the application. As I said, we are using liquid crystal molecule. The advantage is that we can play around or manipulate molecular orientation. For example, for some part, we can make the molecule perpendicular to the surface. The rest, we let the molecule to rotate. Now, when we deform this coating or we decrease the order of this molecule, what happened is that in the perpendicular area, we contract. In this area, we expand. Now, if we're looking under the microscope, you see that we go from a flat coating without any stimuli. If we're shining light, heat, or electricity, we form the ridges on the surfaces. And this is around 10% of the deformation, which means that if you have the coating of 10 micrometer, this deformation is around 1 micrometer. Now, you may think of, okay, you directly see some of the application. Indeed, one of the application we have in mind, from daily life, if you have the surfaces change the topography, there must be the friction must change also. Now, what we are doing here is to test the friction. We have two coating, and then initially they are flat. When we have light, they form rigid, as you saw from the previous image. Now, if you put two coatings orthogonally to each other, like this rigid orthogonally to each other, then actually you decrease the friction when you go from flat to this corrugated state. This is because in two coatings, when they slide, the contact area decrease, and therefore the friction decrease. Then we play around this to put two coatings now facing each other with shining light, rigid form, and the friction decrease. And you can see one of the piece of the glass on the top can now, because of the reduction of the friction, go to the bottom of this slope. This is one application. Another type of application is that in liquid crystal, we can create so-called fingerprints type of structure. And with these fingerprints, we called it because we think it is resemble human fingerprints. It is random and it is unique. Every time you process, it is a self-assembling progress. You never find two coatings are exactly the same. So there are people thinking of using this for security features. Now, but we're looking at the changes on the surfaces. Initially, what we can have with this coating is, again, a flat surface. When we shine it with the UV light, we have these fingerprints popping up from the flat surface. Then we get corrugated surface with fingerprints protruded. In this case, we get 20% of the deformation. Again, meaning if you have 10 micrometer thick film, now the protrusion is around 2 micron. In this case, the coating is around 3 micrometer. Now, what we are using this is to use this shining we have fingerprints grabbed an object. We switch on the light. Because of the friction reduction, we can release an object. This is we use to solve the existing problem in a robotic handling. Now, if you have the hard robot to pick and place object, if your object is fragile, like glass or cook even eggs, and quite often the robotic hand is covered with rubber. Now, you pick up something, you prevent this from broken, but then you have problem during release because the object easily stick to your rubber. Our solution is that if we can reduce the friction of this rubber, as we show here, we can promote the release function of a soft robotic hand in picking and place the object. This is one idea, but now what you saw so far is that we create the surface, we create flat surface, we have surface corrugation, and this corrugation reduce the contact area, then we have friction decrease. But we can also do is that to form the surface like this, to have spiky points forming from a flat surface. In this case, if you have two coatings next to each other, because they can sink down to each other, then you actually increase the friction. And this movie, you can see here, okay, the movie doesn't play, but upon the light, the spiky surface formed and they sink into each other, and you can rotate them to 90 degrees, and two glass plates stick together and doesn't shift off from each other. So we can have various ways to control the friction in a dynamic way. I will switch a little bit to another thing is that again, we see the fingerprints formation. Instead of to control the friction, we can also use this for the touch screen. What we are now doing this is to have the surface formed, dynamic surface. When you touch, give the feedback to the hand. Then you have your iPad, you can do blind typing. For this reason, if you think of we need to integrate on the screen, then we developed electrical responsive system. And we put this coating on electrodes, and the similar electrodes might use for TV, and then we laminate our coating on the electrodes using electrical field to switch. Now, besides that, another problem we always confront the problem we want to solve. It is in this video comes a Mars rover. The Mars rover on the Mars suffer from sandstorm, huge sandstorm. If you have the sandstorm and the solar panels on the Mars rover is covered with sand, and then that couldn't receive the power to power this Mars rover. It is an actual problem. I think 2-3 years ago, NASA lost 2 Mars rover because of sand issue. Our solution is actually to have our dynamic surface continuously oscillate to mechanically remove of the sands. Yet then we can keep our solar panels clean. If you think if this idea works, then instead of more than solar panels, the mechanical component and optical component can be all covered with our coating, and we realize it is the self-cleaning function. This is the idea. To verify this idea, we bought sand. This is microscopic image of the sand, around 500 micrometers in diameter. And this is a coating. You should realize in this demonstration, you see the solar panels is large, but our demonstration from the university lab is only 1 by 1 centimeter. This is 1 by 1 centimeter is the active region. And we covered our coating with sand. This is the white area covered. Then we put electrical field on. You can see that within 1 second, 96% of the sands are repelled from the coating, and which prove our idea that indeed we can use this for self-cleaning aspect. Actually, NASA's agent has been approaching us several times to look into this technology. Now, you're thinking, okay, we are removing the dry sand, but in some other, besides in the Mars, some other real environment, the sands can be wet, especially after raining. We are also hoping to remove the sand, not only dry sand, but wet sand. Wet sand is especially difficult to remove because of the water, the sand and the substrate has the capillary force, which make the sand attach or any dirt attach to your surface strongly. To solve this problem, we can even functionize our surfaces with fluorinated compound. And then with that, we also can just by applying electrical field, remove the most of the sand again. This is the sand removing. And another still, we have these fingerprints. Now you see the surface continuously oscillate to remove the sand. What we can also do is that we create the surface at the beginning, it has already corrugated state. Then we reverse the corrugated states. The high, the peak become valley, and the valley become peak. In this figure, you see better. We have initially this wave, and by light or also by electricity, we put the valley. We put here this peak to valley and valley to peak. Now we do one step further. Initially, at the peak of this coating, we functionize with adhesives. So this is sticky towards the air interface, while in the valley, we functionize with non-adhesive. Now you can see that by reversing this deformation, the non-sticky part coming to the surface, while the sticky part go to the bottom. We use this for release system. And you can see here that initially the red protrusion, we have a sticky state. Then we, one moment. Now, then we shine in UV light and we have the surface reverse towards non-sticky surface. We can reverse back to sticky surfaces. Then we use this surface to pick up an object at the sticky state, and we pick up it is sticky to the coating, and we transport to another place, and we shine in light. Now non-sticky surface become towards the surface, and we can release the object. This provides one more solution for the pick and place. Now in industry or semiconductor industry, the pick and place is really done by the vacuum. Vacuum can also damage your component. For this, we propose another solution to pick, transport, and release the object. Now, from there, I changed the topic. So far, we've been discussing that the surface dynamic changed the topography. We see the surface oscillating could remove the sand, and we see the surface could reverse the deformation, and we use this to pick and release devices. And what we can also do here is that we have the coating to eject liquid from the bulk of the coating to the coating surfaces, as you can see here. In this case, we have also a number of applications I will show you in the next slides. So in order to have the coating that could eject liquid, we form so-called porous coating. Just imagine you have sponges at home that can absorb water in the pores. Only in this case, it's much small, in a nanometer or micrometers size. And this is the porous. We can fill this porous with liquid initially in the bulk. And we eject the liquid to the surface as if you squeeze your sponge to release the water. And what you can see here, it is a video to show that upon UV light, we have this droplet form at the coating surfaces. Not only the entire coating we can eject liquid, but we can also do is a selective area to eject liquid. If we remove this area, we see the indentation because of lack of the material. Instead of using light, again, we can use the electrodes, electricity to eject a droplet to the surfaces. In this case, what you see here is that we apply these electrodes again in the bottom of the coating, and we have electric field on, and in between electrodes we have the highest electrical field, and therefore droplet is ejected in between two electrodes, as you can see over here. Yeah, besides we can use electrodes, electricity, and the light to eject liquid, we can also play around to manipulate. For example, in this case, first we eject liquid by light uniformly everywhere, and then we switch on the electric field. Then we can localize the liquid to the area we like, and we can switch off the field, and eventually this ejected liquid can be reabsorbed back to the coating. And then you can see here, besides in a line, we also can do in a various pattern to manipulate this droplet. Now, I would like to show you this video. Thinking of that, we're working on the fingerprints pattern. We can eject the liquid. We take a better looking at into our human fingertips. You see that we have rigid. We also eject liquid, grease, fat at the coating. And then we were thinking about, we don't know how to use this, but how about mimic this phenomenon? So what we do here, again, we have fingerprints pattern, and in this case, we combine this with liquid ejection function of the coating surfaces. One other thing I would like to point out is that if you look at the ejection of the liquid of human fingerprints, it is always coming from the rigid area. And we also mimic this phenomenon. Here, the lighter blue, it is the rigid. Then we apply UV light. We can exactly eject liquid from also the rigid area of the fingerprints. Now, besides mimic our human fingerprints, we're also using this ejection to have chemical reaction, to realize chemical reaction. For example, what you see here, this glass plate in yellow is our coating adhered to a glass plate, and our coating can eject acid into a base to realize acid-base reaction. Actually, we can eject many other chemicals. We choose this because this is visualizable. Yeah? If we eject acid into a base environment, we have acid-base reaction that generate color. And in this case, it is pink. And you can see here, the pink is starts to forming in this base bus. And that takes some time to see the color uniformly distributed around 5 minutes. It is not because of the ejection. Ejection takes place in seconds, within 5 seconds. However, the diffusion to realize chemical reaction, the diffusion of the color, this takes time. That's why after 5 minutes we see a uniform color. Besides ejection, eject the chemicals, we also eject a drug. In this case, we have ibuprofen could be released from our coating. We can also do antibiotics. For example, we make a smart bandage that on your wound that can release drugs on demand in a controlled manner. And with that, I would like to summarize what we are doing. We are working on a number of topics, especially interested on the surfaces, that we change the surface topography in a dynamic way by light, by electricity. Because we're from Technical University, we always have solid application in mind. I hope here you would appreciate our friction control, the pick and release function device, and we also could eject drugs for smart bandage, for lubrication control, and those are we are interested in. We're of course in contact with medical company, but we're also in contact with virtual reality company because this surface change the dynamics. You can feel, also eject liquid, you can directly feel the changes by your hand. And with that, I would like to thank for my colleagues who contribute to the content of the work, and also a number of collaboration. We have not only European funding source, Dutch Science Foundation, National Foundation, but also a number of industries we work with. And with that, I also would like to thank you for your listening this presentation. Thank you very much. Yes.
Very nice presentation. Thanks a lot. How small can you make these fingerprint features or these radio features?
This fingerprints, theoretically, it can go to infinitely small because it go to atomic level because it is really a self-assembling process. But in the lab, we didn't go to that small because the smaller go to nanometers range. You have more, you need to use more advanced microscopy to look. But it can go small because it's not based on lithography. It is based on the molecule self-assembling, so it is go to atomic level.
Yeah, and for the particle release, you use 550 micrometers
Yes.
for rather large particles.
Yes.
And these were dielectric particles, so it was sand.
Yes. Yes, and the reason choose this particle because this is also a relation between your particle and your
Just to reach out,
size. Yeah. Choose wrong, you may have the opposite effect. Yeah, exactly. Yeah. Yes.
Thank you so much for your presentation. And I was just curious about the last slide you showed us. Can you please elaborate a little bit on the virtual reality?
The virtual reality is like this. You have your goggle and you go to virtual environment, you touch, you in the environment you touch, but you don't have much sense on your touch. You don't feel you touch anything. So what we can do is either integrate it into our material to the gloves, that when you go to, for example, touch something wet, that eject liquid, link to the software of your goggle, or directly have the morphing shape, that if you have a basketball coming, you can feel it to give more touch sensation in that case.
And do you have any examples in your lab?
We are now working with the people from virtual reality working on this. Yeah. And we also we have the example of the haptics, that you don't need the goggle. Imagine that blind people, they don't have e-reader, right? Because the e-reader is to adjust your vision. Blind people need to touch the popping up braille text. Our idea is to have a refreshable. This surface can become protruded and flat, so you can refresh your braille text, and blind people can touch that. This is what we have few samples that you can really feel of the change of the surface. Of course, this is true for the blind people, but in many occasions you actually need the haptics. For example, if you driving your car, you have navigation. If you touch now, it is really the problem. You have to stop and look at your display to type in the location. But then what you can do is that if you have touch sensation and you can somewhat feel your screen where you touch, you put in to write the letter in a good way, and that is also much safer for the users. This is what we are working. And also your mobile phone, your iPad, you can switch on your haptic function, but that is the entire your device. You feel the vibration of the entire device. With our coating, we are hoping that to give you so-called in-screen touch feedback, that you touch this point, only at this point you feel the feedback from your screen.
I don't understand how do you apply your code.
Sorry?
How do you apply your code to the materials?
Yeah, you mean the coating? Yeah. So what we are doing now, at least driven scheme, we try to follow the driven scheme of your television or your iPad. That is a so-called implant switching scheme. That you apply the coating and your electrode is underneath your coating, and your surface could be free of touch. And if something changes, you could feel. Of course, for real device, you need somewhat more protective layer on top. And the protective layer, that is what we are developing. It is really the trade-off. If you make it too strong, then you might not feel your coating popping up. If you make it too soft, maybe that's not strong enough. This is the optimization we're still working on.
How much energy is required in order to create this?
We are not using energy. It is the voltage. There is no current going through.
But for example, the energy of the light rays.
Oh, the light. In the light, still for the deformation, that requires somewhat higher energy. That is 300 milliwatts per square centimeter. That is not safe for human. And also for this reason, we go to use the electrical field. That is much better because you are not exposed to the light. But for secreting, we are using 5 milliwatts per square centimeter, and that is benign to human. You also use UV light for disinfection purpose, right? And 5 milliwatts per square centimeter for the secretion, that's good because we also use this for bandage, that you directly contact the skin, eject the liquid, and that dose is safe.
Yeah, because I was wondering if this could be used in microelectronics with power supplies or microelectronics with small power supplies or with small amount of
Yes, yes. And reducing still, voltage is still a bit issue. Voltage we are using 7.5 volts per micrometer. If you think, okay, I really need to put on my iPad or screen, they are powered by 3 volts per micrometer. So we still need to reduce half of the voltage we are using now. Yeah. Yeah.
Thanks for your presentation. I was wondering, do you also aim to make unique fingerprints, and is there any value to that?
Unique fingerprints. There is, for the application I present here, there's no value, but people also use this as a security feature. Yeah, that you have expensive stuff, you put this, and nobody could repeat, because no matter how much you try, it is every time you come to the different pattern, and can be used as a security feature to the expensive stuff.
Because it's not programmed.
It's not programmed. The
It's
exact.
just a reaction.
It is reaction self-assembled. Yeah, this is the tiny little changes in anything can be different. Therefore, we actually have patent on this. Yeah. Yeah.
What is the cost to produce this kind of material?
The material, you would think of the material is expensive, but actually not, because that's the same material of your display. If you look at your LCD, that is the price you can afford. And actually, we made the calculation, the electrodes is even more expensive than the material. And again, the story is that the more people we have, the more product application we find, the lower cost we can bring. But now with the liquid crystal display industry, we can substantially reduce the cost. Yeah.
Do you already have any specific agreement of application right now?
Agreement with
With companies?
yes.
Is it being used in some products outside where you market it?
Sorry.
This kind of technology is being applied outside
Already. Not yet. Besides liquid crystal, you see many display. What we want to develop here, it is still at laboratory level, but we already have the agreement with the company to develop further. We have agreement with Merck that is developing liquid crystal, the largest liquid crystal company. For haptics, we have agreement with BD, the medical company, to develop smart bandage, those type of. But everything still at a laboratory scale, and of course for university, we are not interested to bring things to large quantity. Yeah, that also we cannot do. For this, we always collaborate, or there are quite some startup from our group doing those things. Yeah. Yeah.
Thank
you.
Thank you so much
Thank
for
you.
your presentation, and
you.
thank you for answering all of our questions.
Yeah,
I suggest we carry on talking about this at the bar. So I invite you all afterwards to go into the restaurant if you like. You're also welcome to stay for the meetup table. I don't know yet what the dish is, but it will always be a vegetarian dish, so you're welcome. Check out the website for our next program. Next week we have Valentine Maurice talking here about social light design. Yeah, enjoy your evening, and thank you again for being here.